Get going here. So today's guest speaker is Dr. Isaacs. Has anybody had Dr. Isaacs for a class before? Okay, great. So Dr. I'm very excited to say that we were able to capture this young man when he was in the job market, what, 2 years ago? 2 years ago. Dr. Isaacs did his PhD work at UCSB. We'll hear about the kind of stuff he works on in terms of control systems with UAVs. But he's a fantastic addition to our campus here, our computer science department in particular, and our larger collaborative aerial and aquatic robotic research group also. His specialty, well, he has many specialties, but one of his specialties is in sort of having these distributed units talk to each other. How do we control these systems in flight and that kind of good stuff. He's got a lot of great research interests. So outside of drones, if you guys are interested in drones and robotics, you should talk to him. For example, he's taken a group of students to the NASA, what do we call it, NASA Robotics Challenge?
Swarmathon.
So NASA Swarmathon. And those students are working on that now, and then they go in April?
Yep.
Go in April to Florida and compete with universities from across the country on sort of a good-spirited competition, right? Everybody's trying to better themselves and learn how to do stuff better. So if you guys are interested in robotics and this kind of stuff, and after this class, if you get more and more interested and want to be more on the mechanical side, design side, you should consider taking one of Dr. Isaacs' classes. Also, Dr. Claveau, who spoke to us earlier, same thing. Some wonderful classes these guys are offering. But in addition to that, Dr. Isaacs has a lot of interest, not just in things flying around, but also in signal processing. He has a project with working with researchers in Africa, trying to help collect audio data from distributed networks and all kinds of great stuff. So I asked him today to come talk to us about how we control these UAVs from a more technical sense. So with that, Dr. Isaacs.
Okay, thank you, Sean. Thanks, everybody. Thanks for having me. I guess if you have too many specialties, maybe you're not a specialist in anything. So that's what I'm on the
That's
danger.
me. I'm not specialist in too many things.
Yeah, I'm in danger of running into that. So, okay, so I'll talk to you today a little bit about controlling UAVs and what that means really. But first, I want to kind of introduce myself. And then we'll talk a little bit about what's in the name. Why am I using the term UAV when this class is called remotely piloted systems?
Right,
You're doing a drone survey. So there's all sorts of weird names about these systems out there, and it kind of helps set the context of what we're going to talk about. Then we're going to get into the kind of the nitty-gritty about how they work, and then I'll finish by talking a little bit about some of the applications and opportunities that I use these things for at Channel Islands. Okay, so I started my undergrad career back at the University of Kentucky. I was not a Wildcat in the suit, but I knew the guy who was in the suit. I played golf with this guy. The years that I went there, we won 2 national championships, and we're in the finals in one of the years. So it's a big basketball school. You probably don't understand being here where we have no teams, but it's very important, and it's that time of the year. Today they're playing their first tournament game. After I graduated with an electrical engineering degree, I went to work for this company, Lexmark, and designed control systems for their printers. In particular, this was the last one that I worked on. And the idea there was we had to take motors that were similar to the motors that drive the propellers on your quadrotors, same type of motor, turn that motor to turn the shafts inside the printer that move the paper through the machine, or that move a belt back and forth to pull the print head that fires the ink back and forth very precisely at a precise speed. So just like when you're flying the quadrotors, you spin the motors at a particular speed to make it be the height that you want or go in the direction you want. We spun the motors inside these little devices to move the paper around. And so the things that I learned about on the job there sort of translated to later in my career when I decided to go back to grad school and study how to control and use UAVs. So my grad dissertation was sort of like Sean was mentioning, it was kind of the marriage of using UAVs with signal processing. So I had a sensor network of these things, which were acoustic microphones, or just not a lot different than this thing, that we had scattered all out in this beautiful area up in sort of central California. And what we were trying to do with those microphones was to measure the sound of explosion. So this was an Army project, so an explosion would occur and these microphones would all pick up that sound and they would all timestamp it. And then if you had a bunch of these microphones scattered out all over the place, you know, you can hear an explosion from very far away, then you can figure out from these different timestamps exactly where the explosion occurred. But the problem with that is when you have sensors like this that are placed on the ground, they have a little radio. Here's the radio. But it's very low to the ground. And so it can't communicate very far. So the sensor nodes, if you needed them to be spread out, they couldn't communicate with one another to combine all this information. So our idea was to use a UAV like the ones up here that had one of the same radios on it, and that radio could communicate with radios very far away because you're up in the air. So the ground has a tendency to degrade radio signals, or trees or anything, mountains, anything like that degrades the radio signals. But if you're up in the air, you have very good radio communications, as long as you can still see the UAV in the air. So you guys have probably been talking a little bit about FAA regulations about you know, you need to fly within line of sight, or you can't fly beyond line of sight, that sort of thing. And part of that rationale is that the radio communication back to the base station actually largely depends on line of sight. So that's one of the things there. And so we flew these UAVs around, gathered the data from these sensor nodes, and then figured out where the explosion occurred, and then flew the UAV there and imaged it. And so I know that you're planning sort of a quadrotor technical challenge. So this is sort of in the same kind of
drone data race.
Drone data race. So we were essentially doing that with two of these. So we had one that was going around and collecting the data and then telling the other one where to go take the picture. And so they were constantly back and forth between these two UAVs that you see there. Now, I didn't do this project all on my own. You see there's a whole army of people up there. But largely the work that was done to tie all this together was myself and a gentleman beside me in the back there named Sriram, and we were the two grad students on this. And we worked with a company in Goleta called Toyon Research Corporation, and they had about 5 guys there who were the crew for the UAVs. So they made sure everything was flying safely, and they made sure they landed safely, and they took off safely, all that kind of stuff. Although this gentleman, Seamus Collins, sliced the tip of his finger off because we were launching the UAV. It was similar, you know, they're similar to that one over there where the propeller is in the back, launching like this, and he didn't get the tip of his middle finger out of the way in time, and he sliced the tip of his finger off. And this is on an Army base up in Central California, and you're about an hour from the nearest town. So it wasn't a pretty picture. And during the week of our final sort of field tests, this happened, and we were really worried that the whole thing was going to be canceled. But luckily, the guy beside him there, Chris, decided he would take the risk and put on like a Kevlar glove, and we managed to do it. So my PhD was, you know, hanging on the tip of Seamus's finger at one point. So, like Sean said, about a year ago, I came, I guess last 2 falls ago, I came to Channel Islands. And last spring, I taught a course on embedded systems. And so embedded systems basically means tiny computers that are embedded inside of something else. So inside your phone, inside the UAVs that you fly, inside the ROVs, inside the 3D printers, all of these things are embedded computing systems. And so the course that I teach, you learn about how do you handle various types of I/O, how do you write programs that can run on small computers with limited memory, limited processor capability. So these little tiny computers are nowhere near as powerful as, you know, even an old laptop, for instance, and they have to run on really low power. So the final project was an autonomous car race. And so the students had to design an algorithm to read from little sonar sensors, which just measure your distance to various objects, and read the wheel encoder on the little car. So there's an encoder here that measured how far each wheel turned and how fast it's turning. And from those two sensors, they had to figure out where they are inside the halls of Sierra Hall and navigate down the hall. So a couple teams made it all the way from one end of the building to the other end in a reasonable amount of time. So it's a really fun project.
So if students want to take the embedded systems class, what's the prereqs? Or are there prereqs?
The prereqs are a bit steep. Really the key is if you've had some form of programming before. So ideally you would have had C programming. So the algorithms that drive this device are written in C, which I know that we don't really teach C outside of sort of the middle meat of the major, which is a problem I'm trying to address. But I'd like to see us teach that at like a 105 level so that students could take this course.
Programming kind of.
Yeah, but right now we do that in Python and another language called JavaScript, and both are fine languages, but it would help me out and help my numbers go up if we had also a C section of that. Okay, any questions about that? All right, that was a little bit of a long-winded story, but so I want to give you a little bit of context about quadrotor history. So I don't know if you've seen any of this kind of stuff in this class, but quadrotors date back to the early 1900s. So this is 1907 was credited with the first flight of a quadrotor type device. And then in 1920, there were, this was the first flight distance record for helicopters of 360 meters. So they made it 360 meters in 1920. And these were, notice there are people flying on these things, you know. There's all this talk out there now about drone taxis and drone helicopter cars and stuff like that. And it seems crazy, but there were guys sitting on these things all the way back in the early 1900s. And then things got a little more improved by a little bit later. This was a device that flew 5 meters off the ground. And then by the 1950s, we had something known as the VZ7. And one of the terms for this is called the flying Jeep. So it could go 60 meters high and a speed of 30 miles per hour. So this was, I can't remember the name of the company who produced this, but it's an Army flying Jeep. So again, there's a pilot in there. Seems like a pretty dangerous spot to be for me, but you know, someone had to do it, I guess. As I referred to earlier, what's in a name? So you hear the word drone, what do you think of? Is that a positive context or is that a negative context? And this may be even one of the survey questions you hear. For me, it's very negative because when I think of drones, I think of blowing up people in Yemen, in a country we're not at a war with, or blowing up people, possibly even American citizens in countries that we're not at war with. I'm not okay with that, but it's what the term drone says to me. But the definition, if you look it up in the dictionary, is a stingless male bee, one that lives on the labors of others, or a parasite. And then the third is an unmanned aircraft or ship guided by remote control or onboard computers. And I found this interesting because I also had in my...
Sorry, I got pushed down, I guess.
Yeah, so this one didn't quite... well, that's okay. No, I think it's just a formatting thing. So let's see. You can try if you want. Yeah. So I found that interesting that they included or onboard computers. So another kind of thing about drones for me, I consider them to be remotely piloted. Mainly because I'm in the business of doing the onboard computer automatic piloting. And so then this definition made it even more mixed up for me, because how do I separate the work that I'm doing where I'm trying to write algorithms to automatically fly these things from the folks who are going out to Fry's and buying one on Christmas Eve and flying it
or Best Buy.
Or Best Buy, whatever. Someone from Best Buy in here?
Maybe.
All right, cool. So how do I separate the work that I'm doing from that when I'm talking to people who aren't in sort of the business? And so this is a relatively new thing about the onboard computers. According to Google, it's a remote-controlled piloted aircraft or missile. And so that was more in line with my thinking before. So what I really want to talk to you about today is really how do these things work? So some of you probably know a little bit about this, so it's maybe repetitive, but I'll just go through it a little bit. So here's just a cartoon of a...
They haven't heard this yet.
They haven't? No. Not at all. Okay, good. So here's a cartoon of a quadrotor, and the way that they work is that the propellers on opposite corners fly together, and then propellers on the same side fly opposite. So these two, this one, fly clockwise, and then this one in the bottom left fly counterclockwise. Okay? And we'll go through what that allows us to do because we're having these sort of opposing forces, if you will. But first I want to let me skip back to that. So we'll stick with this theme right now. So when we have these two flying one direction, these two flying another direction, if all of the things are flying the same speed, then we get something called lift. So this is applying a force in the up direction, and the thing will take off, and it'll go up until you come to some sort of steady state speed where the speed of the propellers apply a force that exactly opposes gravity. Okay? So let me go back to this though, and then we'll get into how you change the other things. All right? So this is what's inside, or was inside a couple years ago. This company's starting to fade now, so
we still have a lot of them.
Not really inside too many things these days. But this is the guts of a 3DR quadrotor, much like the Solo that's up there, and probably some of the ones that are over there. So you have this autopilot, which is called a Pixhawk. You have a GPS, a buzzer that just lets you know that you've loaded the software properly and that sort of thing. You have this thing which is called an I2C bus, which communicates with other sensors such as the pitot tube. You have a current sensor that allows you to control basically it's used to control the speed of the motors. And then you have a radio to radio back. You have one. So here's what the size of the thing, to put it into context. So this thing is only about the size of a little bit bigger than a key fob. Telemetry radio, and then this LiPo battery. Okay, but what you're not seeing here is what's inside this piece. So inside this piece, the key thing that's inside here is called an IMU. Has anyone ever heard of an IMU? One person. What is it?
I can't remember off the top of my head, but it's basically it can sense the area around it, right? It's like a compass.
Not exactly. So it does sense some things, but it's not sensing the same thing as a compass. So an IMU is an inertial measurement unit. And what that is measuring actually is the rotational speed. So if I rotate this device, it's measuring the speed at which I'm rotating it, and in any direction. So if I rotate it this direction, or this direction, it measures those speeds. And if I threw it across the room, it would measure the linear acceleration. So how fast the velocity is increasing as I'm throwing it across the room. So two things that this thing measures is angular speed and linear acceleration.
Have you guys heard of gyroscopes before?
Yeah, you might have heard of gyroscope. So a gyroscope is 1/2 of the IMU. So the accelerometers make up 1/2 and the gyroscope makes up the other half. Good question. Okay, so now what can we do with these two instruments? So some of these equations didn't come through, but
Oh, sorry.
okay, that's fine. So instead of a quadrotor, we'll just use this helicopter here as an example. So when I was saying it can measure the angular rotation speed about these different directions, what I was really referring to is the directions of roll, pitch, and yaw. So if you think about a helicopter, if you think about how if it's oriented like this, maybe I can use this thing.
Ooh, look at that. Some props. Look at
Props,
that.
laying around.
Props.
Nice. So if you're thinking about this, pointing out the nose of the airplane being the x-axis, then roll is this direction. So the rotation about the nose of the airplane is roll. Okay? Now rotation about the wing is pitch. So if I'm pitching the nose up or pitching the nose down. Okay? And then the final thing here is yaw, which is rotation about the center in this plane. So this is the yaw component. All right? And so these kind of systems, this is going to be a little bit of math, so I apologize. And then don't worry about it. You're not going to be tested on it. Just ignore this.
Don't apologize.
So,
That's cool.
So these kinds of systems obey Newton's second law. So how many people have had physics where you learned about F equals ma?
Come on, don't lie.
No one?
Oh, liars.
One person? You don't have to take physics here at all?
They do.
They do,
Yes.
just not yet. Okay, so anyway, well, this will be a crash course in F equals ma. So we have F equals ma. So you apply some force. This is some mass. And then that results in some change in the x direction here. Okay? And so,
So
is there
equation's
no
screwed
good?
up?
Yeah. Yeah, well, maybe I can just explain this in. Don't worry about it. Yeah, I'll just explain it. So, if we have this original formula here, which is x equals 1 over m times the force, does anyone know if you have, so these x's are the positions. So does anyone know if I have position, how do I get the velocity? What's the velocity mean if I know position?
Speed over ground.
Speed over ground, yes, but in terms of the
A generic position.
generic, if you just had a generic position, how would you calculate the velocity? What does the velocity mean? It's in meters per second. So what that means is it's the change in position with respect to time. Okay, so how quickly my position is changing with respect to time. And so if you want velocity, you should
You wanna
those equations. That's okay. So then you take the derivative of the position, okay? And well, don't worry about this. I wasn't even going to go through this anyway. So then, if you want, if you take another derivative, what is that? Does anyone remember that from physics?
Acceleration.
Acceleration. So the acceleration is just 2 times the derivative of position. Okay? So if I have something that measures position and I want the acceleration, I take the derivative twice. Well, what did I say that this thing measures? Does it measure position or acceleration or velocity? Well, it measures angular velocity, but what about linear? What about when I'm throwing it across the room? What's that? Acceleration. So this measures linear acceleration, but we don't really care about what the acceleration of our quadrotor is. We care about where it is, right? And so the process for figuring out where it is what's the if you take the derivative twice to go from position to acceleration. What if I have acceleration and I want to get position? What's the opposite direction? Anybody remember that? Okay, so so if you have acceleration and you know that it's 2 times the derivative of position, to get to position you take the integral twice. So it's the double integral, and that's what used to be here. But it's not important. But so the takeaway from this is really that the math to go from acceleration to position is fairly straightforward. You just take the integral twice. Now, one problem with that is the accelerometers on these things are kind of noisy. And so very quickly, when you're doing this double integration, you're also summing up all that noise. And so when you sum up the noise and then you sum it up again, then the noise tends to grow. And so if you're only relying on figuring out the position of this thing based on the acceleration, then very quickly your notion of where you are gets off. And this is called IMU drift, if you hear that term. And oftentimes IMUs will spec their drift with respect to time. So this thing will be off by X number of meters in this many seconds, that sort of thing. And what that really says is this is how noisy the acceleration's measurements are.
So noise is one term. Another term is error.
Error.
Talk about
yeah.
positional error. That's another way to talk about it.
Yeah. So the in reality the acceleration error, any errors in the acceleration measurement get sort of amplified when they get summed up twice, and so that results in a big position error. Yeah.
Is that why you call it drift too? Because it like drifts away from
Mm-hmm.
Where you really are from where you think you are gets larger and larger. The error gets larger and larger. So that drifting of the error growing is where that term comes from.
Drifting off course kind of thing, right?
Yeah.
Like if the rudder on the sailboat was a little messed up and you kind of keep going the other way, yeah.
Okay, so that's the double integration. I don't know what those symbols are. Okay, so there's a similar concept for this double integration for angular stuff as well. So we were just talking about the linear position, the linear velocity, the linear acceleration. So there's a similar thing for rotation, but it has to do with torque. So instead of force, the notion of force, but in the angular world, is torque. So this is putting a twist on something. So when you slam a door by pushing it, you're applying a force. But when you open a door by twisting the doorknob, you're actually applying a torque. So when you twist something, that's applying a torque. Okay? So don't worry about any of these kind of things. But basically what the takeaway here, though, is that to get this angular acceleration, there's a formula that's the torque equals I times the angular acceleration. And then this is the formula to get angular velocity. But we already know that we can measure angular velocity, right? This thing can measure angular velocities. It's not measuring angular accelerations. It's actually measuring angular velocities. So we actually get to start with this equation, and then we only have to do it once. So I asked the question here, what's the angular position? It's really just integrating this thing one more time. So this is the measurement that we're getting from the IMU. We integrate it, and we'll get the angular position. So this is how you get the roll, pitch, yaw. Okay? Now, as a result, the gyro is a somewhat better instrument to use than an accelerometer. Why? Keep in mind, we only have to integrate one time versus two, right? So the noise on the gyro only gets amplified that one time, where the noise on the accelerometer gets amplified 2 times. And so typically gyroscopes are a little more trustworthy in terms of what they're giving you than accelerometers. Okay, back to the quadrotor. So this is, all of that was just to talk about this. Okay, so again, we have the quadrotor. We have the opposite corners rotating the same direction, but opposite from the ones on the same side, right? So 2 are doing counterclockwise, 2 are doing clockwise. Now if we want to go up, what we should do to go up is what? Anybody want to take a guess?
Equally.
Do them all equally, exactly. So if we spin all 4 rotors the same speed, we're going to go up. And now that going up applies some force in the up direction to the center of the quadrotor, okay? Provided they're all balanced and that sort of thing. So you're pushing up, and now you have gravity pushing down. And so there's some speed at which you will balance out the down force of gravity with the up force of the thruster, and you'll hover. And so that's the basic hover controller, is to set the speed to balance out gravity and hold one spot. Now if we want to rotate in the yaw direction, what we do is actually reduce the speed of the clockwise rotors and increase the speed of the counterclockwise rotors. And what that will do we have a quadrotor?
Want this one?
Or here's one. Here. So what I'm talking about here is we.
Hey, look, just pull it. Not that we're gonna have a problem, but let's just be super safe and pull it.
Oh yeah.
Better, yeah.
Thank you. So to orient this picture, so if we take this one, and these two are spinning together, reduce their speed relative to these two. So these two are spinning faster than these two. That's going to cause the quadrotor to do this maneuver. Okay? So that's what's going on when you apply the stick to do a yaw maneuver. Now, if we want to do pitch, what we do is actually reduce the speed of these two relative to these two. So what's that going to do? These two now are going faster than these two. It's going to cause this, right? So it's going to cause lift in this direction, and more lift in this direction than in this one. It's going to cause it to rotate about that. Similar for roll, you just make these two faster than these two, and you're going to do this. Does that make sense?
Okay. So you can imagine how hard it was back in those pictures from the early 1900s to make this work, right? Because there's no computers to sense what was going on. It was the dude in the middle with levers.
With a bunch of sticks, yeah. Yeah. Okay, so now it gets down to what I like. So the set point, so we're going to talk about closed loop control, but I'm not going to do any of the math. So if you want to learn about the math of this, take my embedded systems class or come work with me in the summer or independent study or something like that. So like I was saying, that if you wanted to fly at a particular height, let's take the height for example. Let's say that you want to fly 2 meters off the ground, then that is our set point. So we have some set point that's 2 meters, all right? And then we look at our sensor measurement from our system. This is our system. And we have some sensors that measure how high we are off the ground, either from the camera or from a GPS or from the IMU or some combination of all those things. We get some measurement of how high we are off the ground. And we look at that and we take the difference. So we say we want to be 6 meters, but we're really 1 meter, or excuse me, we want to be 2 meters, we're really 1 meter. So now we have a 1 meter error. And so that 1 meter error gets fit into something called the control calculations. Have any of you ever heard of a PID control?
Yeah.
So that's sometimes tossed around in the context of autopilots. So basically what the PID controller does is says, feed me some error signal, and I'm going to run some calculations and on that error signal and generate an output that is how fast to turn each of the motors. And so that's what I'm calling the actuator output. So the motors themselves are what we call actuators. So the IMU is a sensor, and the motors and the propellers are the actuators. Okay? And so the control calculation says, okay, for an error of 1 meter, then I need to increase the thrust by this much. And now as you increase the thrust, the error gets smaller and smaller, right? So I'm going from 1 meter up to 2 meters. And as that error gets smaller and smaller, then the output starts to go down because the error isn't as big anymore. So as you get closer to the actual set point, the actuator output, or the torque on all the motors, goes down until you hit this perfect spot. Okay, so that's sort of in a nutshell how this works. I don't want to go into all the math of it because it's lots more derivatives and integrals and things like that. So but this is something that's already very well worked out on products like the DJI or the 3D robotics products, or any commercial autopilot already has the PID controller to do this thing very well worked out. Where it gets interesting is now this is the set point for, say, the position. Okay, so if we want to fly waypoints, then the set point could potentially be the position. But where I come in is now I wrap another control loop around this whole thing that says, okay, I want to maximize the radio signal that I'm receiving, or I want to maximize the number of pixels that I see of a particular object that I'm trying to image. Then how do you change the set point to make that work? And so then you're relying that you have some working autopilot that can fly the thing to the set point or to the waypoint, but then how do you do the same kind of calculations to make the sequence of waypoints be sort of an optimal thing that you want? So I'll talk just briefly about some of the things that I'm working on and I have some students working on now. So one thing that I've started looking at once I came to CI is the use of UAVs for precision agriculture. And so this is a sensor called MicaSense Red Edge, and it has 5 cameras on it, and it can measure red, green, blue, near infrared, and near red. So 5 different images. And what this is useful for is if you fly it over a crop, you can look at the differences in these wavelengths. So here's blue, here's green, here's red, red edge, and near infrared. And you can look at something called the typical plant reflectance, meaning what's the intensity of each of those channels for a particular plant. And if you start taking ratios of that, then you can start to calculate things related to the plant's health. And so this is called a Normalized Difference Vegetation Index, so NDVI. And so if you flew over this field that has sort of strips of healthy and unhealthy wheat, I think this one's from wheat, and process the images according to this pretty simple equation, which is just near infrared minus red over near infrared plus red. So it's a simple ratio that you're taking. Then you can get images that look like this, where I think the green is the healthy areas and the red and the yellow are the less healthy areas. And this is something that's been studied for a long time. Hold on just a second. It's been studied for a long time using satellite images. So people have been taking satellite images of crops for a long time and processing them over many hours, and then producing reports about the health of various crops. But there's problems with that, in that if it's a cloudy day when the satellite actually passes over, then the data is not as good. There's big delays between actually taking the data and actually getting the report. And so there's a hot new industry related to this, where people can come out on any old day, fly the thing manually with remote pilots, take the data, and produce a report for the farm owner right there on the spot, basically. And they can make decisions about fertilizer, about pesticides, about anything like that, water, all those kinds of things. You had a question?
Yeah, is that similar to the classification tool in GIS, where we take satellite images and then have to drop polygons and program it to recognize colors to say that's a coastal shrub, that's an oak woodland, or something? Or does it automatically just by the infrared color, you know if it's a healthy or not healthy?
Well, it's from this formula. So this formula is looking at the intensity of each pixel in the image, and they take the near infrared pixel and the red pixel, and they look at the value or the intensity of both those pixels. And where a pixel is just one dot in the image, right? So this is one pixel. You can't really see it there, but each little, how many pixels per inch now is it? Millions. So in the camera, each little dot here is represented by this. So you take the near infrared intensity, subtract off the red, divide that by near infrared plus the red. And that, then the level of that ratio indicates some notion of health.
So what you're talking about, Greg, it's similar. What you're talking about is we're trying to look at a landscape that's very heterogeneous, and we're using the different all the different spectra, all the different wavelengths, and we say, the thing that's half orange, half blue is a cactus, and the thing that's mostly purple is a grass. And we do that. So that's what you're doing about training. If you look at here, what Jason's doing is they're just talking about a monotypic crop, so it's all the same plant. So we're not trying to say, is this category 1, 2, or 3, and we're focusing on the red. So it's basically redness. So it is a much while that can collect a broad amount of data, usually you're using a subset of the data, and you're just saying which of the things in this picture, which one is more intense. Really green is what it really is. They use red, but it's really good. The chlorophyll. Is that a lot of chlorophyll, or is it stressed? Meaning, is that chlorophyll being is the energy that would otherwise be used to make the structure that is the chlorophyll being used to do other things, so stress proteins, go into the roots, all this and that. So this is a relative scale, whereas what you guys do in GIS is more of a categorize everything on the planet kind of scale. Does that make sense?
Yeah, but back
Just
to
by the color, it's already known if it's for the type of crop. If it's a certain color, knows to be healthy or not. You don't have to train the program to realize that that's healthy.
But I think what you're talking about is an interesting. There's two interesting things about your question. One is this is flying at a very high level, right? So you're flying very high, and let's say that you're flying very high and you see mostly green, but you see this little bit of red here. But it's kind of low resolution because we're flying high. So something that's interesting to me is, could I train an algorithm to say, hey, I spotted an anomaly here. I spotted a little red area right there and amongst an area that's mostly green. That could be the start of something. That could be the start of a parasite. That could be a broken sprinkler in that area that we need to go repair, those kinds of things. So what I'm interested in is, can we process this data on the fly and train some sort of algorithm like you're describing to figure out these anomalies and actually fly lower and then get a zoomed in area where the image has lots more pixels in just this little area than the 4 or 5 that are there now that are red. So that's something that we're sort of in the beginning stages of. I have a capstone student right now working on just the basic principles of pulling the data off of the camera and doing the basic processing at this level, and then sort of the next phase will be training some algorithms like that. Good question. One other thing though, you were talking about in the heterogeneous crops or heterogeneous landscapes of plants. I think it would be interesting to see if there were ways to automate using all this extra IR information, because this profile here could be different for different types of plants. So we're just thinking about it in terms of a stressed plant versus a healthy plant, but it may very well be that a cactus has a totally different profile than an oak tree. So it may be that could be useful as well to separate different patches.
We're just putting in a pre-proposal with the DoD to help them do veg mapping on some Department of Defense lands.
Mm-hmm.
So this would be a fun one if we get that money, but it's basically to compare satellite imagery to doing this for gross veg classification. So I should talk to you if that thing goes beyond the pre-proposal stage.
Yeah, cool. So yeah, we can set up some flights with our camera. Yes?
Do you think that, maybe in the relatively short distance future that we'll be able to tell like if there's certain weeds within an area of crop that we need to like go extract an invasive species that's starting to pop up, or is that kind of what you're talking about?
Well, that's sort of what I'm talking about from the zooming in standpoint, right? So it may be that, you know, this is in the context of healthy plant versus sick plant, but it could very well be that the colors don't represent healthy versus sick, but just two different types of plants. But it may be that you have a small outbreak of this invasive species here. Can you detect that and zoom in and actually get more detailed data than just like the basic flyover satellite imagery kind of thing? So yeah, I think it could be possible. It's just, it's not where I feel like the industry is right now, and not where the industry's really going right now. The industry seems to be going in the direction of still remotely piloting and then quickly generating reports. And unfortunately for all the business of UAVs, it seems to be that there's not a lot of money anymore in making hardware, but the money is actually in access to the data that they're capturing. And so lots of the companies are focusing purely on capturing the data and generating the reports, but not necessarily doing as much innovative stuff to try to look for ways beyond just flying the basic pattern above everything.
So I'll just say real quick, that's the purpose of our drone data race, right? To try to interject some more thought, and it's not just about the piloting, collecting it, it's also about thinking about what you're doing with that data and how are you going to provide data in a more effective way. But people are totally interested in that exact question. How can we automate this sort of, what our eyeballs detect, how can we automate that with these systems?
Yeah. And it's not an easy problem. It's a kind of open problem. Yes?
Yeah, I think you may have kind of just answered it, but given that like plants, different species have different like ratios and everything, do you have to like adjust it before you go out and map a certain field of crops, or is there can you kind of just generalize what a healthy plant is?
Oh, that's a good question. So
If it's like a control maybe.
no, I think it would need to be crop specific in terms of what this scale is probably a crop specific thing. I don't know too much about the sort of ag science of this. I'm just kind of getting started in that. But I imagine, yes, that the ratio would need to be different for, say, wheat than it might be for, I don't know, corn or something like that.
So some of the folks that do this stuff more on the more ag science side are pessimistic about this approach right here. I think they're overly pessimistic, but they're pessimistic because for that exact reason. Some things are fine. Other things you can imagine, say like an avocado tree, that the leaf is really, it takes a lot to make the leaf, and there, it takes months to lay the structure down and this and that. And so what they say is when they generate a map like here on the right that shows the stressed leaf, it's not helpful because at that point it's so if there was a more water or a more fertilizer, whatever the intervention was, you would need in some of those crops you'd need to have had the intervention like 2-3 months ago, and that you're seeing kind of the analogy of you're seeing someone cough up blood, and really we should have treated the disease before it got to that stage. But just because they think that doesn't mean it's true. There's tremendous value in this kind of stuff.
So yeah, to kind of second that point, I think the people who criticize this are right in that it is a little late sometimes. By the time you get a huge patch of red, then it may be too late to save that, and the only thing to do is go plow it up and saw it down and replant. So that's why I'm interested in spotting the tiny spot of red and hopefully being able to take action sooner. And so that's kind of where the angle I'm coming at this from. Okay?
So is that a question?
Oh, was there more?
No. Okay.
One other thing, so Sean mentioned this briefly. So this is very much related to what I did as a grad student, but now for a much cooler reason than for the Army. Originally, I talked about how we had microphones and we had UAVs flying around, and they could figure out where the microphone was based on the sound of hearing the explosion. Well, I was contacted by a guy who studies primates in Tanzania, who found my thesis somehow, and I never dreamed anyone would ever find my thesis. But he found my thesis and he said, hey, I want to do the same thing but with chimpanzees. So I want to build a sensor network of acoustic sensors, put them in treetops, and when chimpanzees are calling to one another, they're very loud and you can hear it echoing throughout the valley. So I want to be able to use UAVs to localize and acoustically monitor chimpanzees. No, he's a guy protecting them. He's not a poacher. So
negative, Greg.
The interesting thing about this place is that where these chimps live, it's imagine have you guys ever hiked back in Santa Monica Mountain area, like up where Sean lives? You have all these sort of hills and valleys, right? And so that's sort of how the area in Tanzania where they're studying these chimpanzees looks. The only difference is down in those valleys is pretty dense forest. And then as you get up on the hillsides, it's sort of very limited trees and stuff like that. So because the chimps live down in these valleys, but they have to cross mountains to get to the next valley. And then if you want to go study them, you got to cross another mountain to get to the next valley. And so all these valleys are sort of interconnected, but they're dense forests that are hard for the researchers to go through to find the chimpanzees. So ultimately they want to find them and observe them. So what they're wanting to do is now to use a UAV. Oh, I should have said this is a collaboration with Alex Peel from Liverpool. So they want to use the UAV in combination with the sensor network to actually figure out where the chimpanzees are, which valley they're in, and then that way they can inform the people who are going there to observe them of where they need to go next to do their observations. And there's some value in just tracking which valleys they're in when, independent of that. But that's sort of the notion. So it's a very similar problem to what we did with the acoustic explosion localization, but now with chimpanzees. Yep.
So with the radio UAV, like going in that same path, would it just like collect all the information from the sensors because it's like
Yeah, so it's just a relay. So I don't have it drawn here, but this would be communicating back to some base station because it's up in the air, and we can put a tower near the base station that can communicate with the UAV. And so these are down in the valleys, and they can't communicate back to the base station. So as this guy flies over, then as it's flying over, uploads the data from the sensor and then continues to the next sensor. Yeah, good question. And I have it drawn here with the second one with the camera. May or may not have multiple ones out there, but you can think of, instead of dispatching a camera UAV to that area, you could actually dispatch a crew of observers to go there to look for the chimps. So this is ongoing, and I'm looking for help actually on this. But more at this stage on, we have sort of the parts for this in my office, and I have it sort of put together on my desk and sort of working. But the next phase is I want to go out to Cam Park and actually put the radio on the UAV and make measurements about how far away we can be from the sensor node and still make the communication link and all that kind of stuff. So I'm looking for people who are interested in working on that.
I obviously sound like a chimp, so I'm always willing to.
You could come out and be. You could be the callback, yeah. And this is another project that you guys probably know Tim Holcomb, who's probably in this lab more than he's in any of the CS labs. But I did manage to get some money to hire Tim last summer and Chase to modernize this big beast of a fixed wing UAV. And so they took all of the old, outdated, extremely expensive parts that were in that. And this was produced in the early 2000s by Northrop Grumman. And they took all of these parts out, which were probably tens of thousands of dollars worth of components, and replace them with this first picture that I showed you. This stuff. So they basically bought a 3D robotics kit of autopilot parts for a couple $100 and replaced the thousands of dollars worth of equipment that was in that UAV. So that was kind of an interesting project. They finally have it where it could be flown now, and I don't think anyone's really ready to fly it yet because it's pretty big. Anyone in here feel like they've learned enough that they're ready to pilot one of these big?
Daniel's starting to work on the fixed wing, so who knows?
Oh, okay, good. So I'm looking for someone who's brave and wanting to pilot this thing later on.
It's a beast. So that was the one, right? That was the one we talked about that started us going down this road, that these guys wanted to donate to the university. President was,
So I blame this thing on me getting hired here. So I say that without them getting this gift, they might have never known that they needed someone like me to be at this university. So
to make it work.
Yeah. So it's sort of an anchor in my lab, but at the same time, I kind of feel drawn to it because I may not be here otherwise. So that's it. So yes.
How heavy is that?
It's not that heavy, actually. It's made of carbon fiber. I mean, it's a few pounds. It's heavier than these foam things, but it's not like too much of an anchor. You can come down and check it out sometime if you want to look at it.
We have two.
Yeah.
We're given two.
Briefly.
Yeah.
Really neat though.
What's that?
It's really neat.
Oh yeah. Well, you can come check it out.